All right, guys, just to kind of recap this idea. So let's say we have two magnets. When those two magnets are as far away from each other as physically possible so that there's no interaction between them, we define them as having zero potential energy. Keep in mind there is a certain amount of potential energy they have, but to prevent us having to know what that potential energy is, we define that as having zero potential energy, because really what we're looking at here is the change in potential energy. We don't actually care what the values of initial and final potential energies are. So we just say initial potential energy is zero. As these two magnets come closer together, they're going to start attracting to each other. And as they attract, they are going to release potential energy until they stabilize at the lowest potential energy point. This is where the magnets are actually connected to each other. But if we keep pushing those magnets closer to each other until the point where south and south and north are lined up, they're going to repel from each other and they're going to increase potential energy. So notice up here they have more potential energy than where they initially started. That's because here there's no attraction or repulsion, and up here there's fully repulsion. And if you take two magnets and they're repelling each other and you put them next to each other, what are they going to do? They're going to try to push apart from each other or fly apart from each other. The same idea is going on with an atom, except what we're dealing with is the attraction forces between protons and electrons. So here, the atoms are as far away from each other as physically possible, and therefore the protons and electrons are not attracted to each other in any way, shape, or form. They're not close enough for attraction. So think our force of attraction equals Q1 times Q2 over our radius squared. If the radius is too big, there's no force of attraction whatsoever. They're not close enough to attract to each other, therefore they have zero potential energy. But as this radius gets smaller, the force of attraction is going to increase until they hit the highest force of attraction they're going to be able to do, which is where a bond is formed and the lowest potential energy and where they are stable. But as these atoms come closer and closer to each other, the nucleuses get closer to each other and the electrons get closer to each other, at which point in time we start having this repulsion force of nucleus to nucleus repelling each other and electrons to electrons repelling each other. At which point in time potential energy is going to increase until the repulsion becomes so strong that it's going to fly apart and the atoms are going to separate back to point zero. Now, something to keep in mind is in technicality, this little dot here is flexing back and forth. So a bond is never still. We've talked about solids vibrating, atoms vibrate, and bonds vibrate. So in technicalities, this is moving back and forth and vibrating. So we need to recognize that this allows us to calculate bond length. So notice down here on our x-axis, we're talking about internuclear distance. What does that mean? That means bond length. In the simplest form, it is bond length, okay, in picometers. Also could be in angstroms, but a lot of times measured in picometers. So this bond length is an average bond length. Okay, and you'll see that word average bond length in just a little bit. So this average bond length is because it's vibrating and moving. The vibration is actually what allows us to do some of our analysis in OChem. So the bond bouncing back and forth allows us to analyze a compound and determine what type of bond it has, whether it's double, single, triple, etc. And it allows us to do some other analysis to figure out what type of functional groups and different things are in the compound. So we'll deal with that in OChem when we talk about instrumentation and analysis of compounds. But I want you to understand that it exists, bonds vibrate, and therefore bond length is an average. Okay, the next thing we can do is we can actually determine the type of bond by the amount of energy that is lost. So time, let's refresh. So when these atoms come closer together, potential energy is decreasing. What does that mean? It means energy is being lost while a bond forms. So that gives us a negative delta H, or exothermic. So we've always talked about bonds forming is exothermic, bonds breaking is endothermic. Why is that the case? Well, because potential energy is being released as the bond forms because it's becoming more stable. It doesn't need that potential energy anymore. And then, of course, if we want to break this bond, we have to add energy in to separate the atoms again, to break that attraction force. Where is this energy going? So its potential energy is disappearing. It's going away. Okay, it's being released. Where is it going? Well, potential energy is being turned into kinetic energy, which means when bonds are formed, kinetic energy is released, and therefore temperature is going to increase. Now keep in mind it's a little bit more complicated than that, because a lot of times we're dealing with reactions where bonds are breaking and bonds are forming, and there's a balance to how much energy is required to break the bonds and how much energy is released when bonds are formed. So when we talk about a reaction being exothermic or a reaction being endothermic, we're talking about both processes put together and looking at the net energy gained or lost in a reaction. So we'll come back and talk about that in a little bit. But what we need to recognize is that bonds forming release potential energy, turning it into kinetic energy. Bonds breaking, we have to put that energy in to get them separated, and therefore endothermic. And that's kind of where we are right now. Okay, let's keep looking. We can use bond energies to calculate enthalpy. So up to this point in time, there's going to be several ways we're going to look at how to calculate enthalpy. The first way we've already looked at is calorimetry. Okay? And I forgot the R there. There we go. The second way we're going to be looking at this is looking at bond energies, or bond energy. Okay, and then we'll look at the third way, which is going to be Hess's law, and we'll look at that in a later video. And yes, Hess's law is an S''S. Okay, it's kind of annoying, but that's the way it's written. Anyways, going through bond energy. So what do we do for bond energy? First off, we take the bonds of the reactants and sum. Remember that weird little capital E thing means summation. Okay. So we're going to take the sum of all the bonds of the reactants and subtract the sum of all the bonds of the products. Now the reason being is all of our bond energies are positive, or they're given in positive numbers. And again, what we're looking at is the difference of the bonds from starting at 0 and where it ends up once the bond forms. Okay, and notice, actually we'll come back and talk about that in a minute. So we take all the bonds, subtract them from the bonds of the product. The reason we do that is bonds of the reactants require energy to break, so the reactants must be broken. We must break these bonds. So therefore, this is a positive delta H. So these are already positive, so we put them first in the equation to keep them positive. Okay. We're then subtracting the bonds of the products, and that's because these are forming and therefore releasing energy. So exothermic, negative delta H, this negative distributes to all of these bond energies, making this statement negative or exothermic. So that's why this equation is set up this way. Okay, and I'm showing you that because another equation is, actually most of the equations we deal with in this chapter are products minus reactants. This is the only one that's reactants minus products. Also keep in mind this equation is not on your formula sheet. It is one you will be required to use and will need to know, but it's not on your formula sheet. So just kind of keep that in mind. Now, what in the world do we do with this? How do we look at bond energies? How do we come up with the bond energies? Well, we're given the average bond energies for each type of bond. Now what we have to do is draw the Lewis dot structures for each compound to figure out the types of bonds in each structure. And yes, you have to still be able to draw Lewis dot structures. Okay, so very quickly, if you want to, actually what I want you to do is stop and draw the Lewis dot structures for all 4 of these compounds, and then we'll come back and work through the problem in just a minute. Okay, so methane is CH4, so all single bonded carbon to hydrogen. Okay, we then have 2 oxygens, which is O double bonded to oxygen. And notice I'm not really playing with my valence electrons, I'm just looking at the bonds themselves, but these would, yes, have 4 dots around each oxygen, if you're curious. Okay, that's going to go into CO2, which is double bonded to 2 oxygens. Okay, and 2 waters, which is oxygen single bonded to 2 hydrogens. Okay, now what do we do with that? Well, we look at our reactants first. We have 4 hydrogens single bonded to a carbon. So each one of these is going to have a bond energy of 413. So we take 4 and multiply it by 413. Okay, we're then going to add to that 2 double bonded oxygens, which is 495. Okay, and that is the sum of all the bonds of the reactants minus the sum of all the products. So our products, we're going to have 2 oxygens double bonded to a carbon, okay, which is 745, okay, plus 4, and the reason it's 4 is because we have 2 waters, okay? 4 single bonded hydrogens, 2 oxygens, which is 467. Okay, and we add those up. Now, what I want you to do is I want you to pause the video again before we actually do this math. You can do the math. The math is easy peasy. I'm not worried about that math at all. But what I want you to do is come over and look at these numbers. I want you to hypothesize why the HC bond is weaker. Okay, and how do I know it's weaker? Because it's less stable, it's got a lower bond energy, and why HO is stronger. Okay, so take a second and think about that. Why is H bonded to carbon, single bonded, going to be a weaker bond than hydrogen bonded to oxygen? So take a second, think about that, and let me know your answer. Okay, so the answer here comes down to Coulomb's law, which remember is force of attraction is Q1 times Q2 over radius squared. This force of attraction is going to tell us the strength of the bond. Okay, and the strength of the bond is going to relate to the stability. The more stable it is, the lower the potential energy that's released, or the more potential energy that is released, therefore it is going to have a higher bond energy. Okay, so think back to this guy right here. The stronger the bond, the deeper this curve is going to be, therefore the biggest difference between this 0 and this bottom point here, which is our bond energy. We basically take the absolute value of this difference and make it and that's our bond energy. That's how we get bond energy. Okay, so why would hydrogen to carbon be weaker than hydrogen to oxygen? Well, it comes down to size. Okay, it comes down to this radius. Oxygen is a smaller atom, therefore radius is smaller for oxygen, and therefore going to result in a higher force of attraction. Therefore, it is a stronger bond. Therefore, it's more stable, and therefore it has more bond energy. It is a stronger bond, so it has more energy or releases more energy when it breaks, or requires more energy when it breaks, releases more energy when it forms. Okay, so when we go through and do this math, easy peasy math here. So we have 4 times 413 plus 2 times 495. And I always do this in steps because otherwise I end up doing something stupid with my numbers and subtracting the wrong thing or adding the wrong thing or whatever. Okay, and that is now going to subtract 2 times 745 plus 4 times 467. Okay, which is going to be a value of 3,358. So time, pause, look at this. This is the bond energy of our reactants. Okay, this is the bond energy of our products. What do you notice? The reactants have less bond energy than our products. What does that tell us? That tells us that the bonds of the reactants are overall, or on average, weaker than the bonds of the products. The products are stronger overall. Now, let's see what this gives us. So, 2,642 minus 3,358 is going to give us a value of negative 716, and that's a delta H of reaction is negative 716. Well, what does this negative mean? It means it's an exothermic reaction, which we knew because it was combustion in the first place. But time, what does an exothermic reaction mean in terms of bond strength? Okay, an exothermic reaction is always going to tell us that the bonds of the products are on average stronger than the bonds of the reactants. Okay, so what does that mean for an endothermic reaction? An endothermic reaction is the reverse. Endothermic reactions, the reactants are always going to be stronger and the products are always going to be weaker. And again, when I'm talking about weaker and stronger, I'm saying on average. It's looking at the whole of the reaction. Okay, so in other words, these guys, our products, are more stable. Our bonds in the products are more stable on average than the bonds of the reactants for exothermic. And endothermic, the bonds of the reactants are stronger on average, or stabler on average, than the bonds of the products. Okay, so easy peasy, not too bad. Let's pause here and we'll move on in just a moment. Thanks, guys.